session is on the advanced polynomials. Already on Monday, Khonit Bhaiya has already taken your class on basics of polynomials. So today's class will be taken by Rathindranath Karmakar Bhaiya, and I'm sure you've already seen the introduction for him on the group. So first of all, the only thing I have to say right now is to I'll thank him for taking a session on this topic, and uh, we from the end of all of us, we thank him for taking out time for us and teaching us all this. Now we can begin, I think.
Okay, so hello everyone. Hope you all are doing well. And this is my first time giving a live lecture. I have only done pre-recorded lectures so far, but we have to manage with slides because I don't have a touch pen right now. So we will do great if we interact with each other properly. Ping in the chat whenever you need to raise a doubt. You might also raise your hand, but I prefer pinging in the chat. You are free to text or unmute yourself and speak when asking a doubt. While teaching, I will highlight text using a red rectangle whenever I need to emphasize a point. Mainly the topics are the ones the topics which I mentioned on WhatsApp, those are the ones which we will cover. If time permits or if you are willing to extend the class, we will cover some additional topics. They are purely additional, I mean, they are a bit more advanced, so you need not follow them right now. It's good to know, however. And please ask questions and interact with me because I don't know most of you. So unless you ask me, I won't know. So let's start. So can everyone hear me?
Yes, yes.
Yes, Dada.
Okay.
Yes, Dada.
I mean, ping in the chat if you can hear. I mean, uh, keep yourself muted unless I tell you to unmute yourself. Well, okay. So I'm sharing the screen. So let's start. First, we will begin with the basic definition of polynomials. I know Juanita has discussed them with you. So one of you please answer what is the definition of a polynomial?
What happened? All of you know what is a polynomial. Please answer.
Dada, will I?
Yeah, please.
A polynomial is an algebraic expression that can be expressed in the form a n x to the power n plus a n minus 1 x to the power n minus 1 dot 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 till a to the power a0, where a1 a n minus 1 a n minus 2 till a0 are all real numbers. Real numbers, it can be complex also, and the power exponents are all are not imaginary numbers. They have to be real numbers. Integers, they have to be integers.
Exponents must be non-negative integers, right? So
Integers.
okay, next time I ask you, don't unmute yourself. I mean, write it in the chat because if two of you start speaking at the same time, then there will be bandwidth issues. So you can write as much as you want. I don't mind. So okay, that's basically correct. So the simplest way to think of a polynomial is as a function which involves sums of non-negative integral powers of x, where x is the free variable. Now, this is a very naive idea of polynomial, but this is the basic definition and it works pretty well in certain situations. So, in many problems, the only thing you have to do is to merely treat it as a function and substitute a few values into the polynomial and view the obtained equation merely as you would view any other algebraic equation, ignoring the fact that they involve only powers of x. What I mean to say is, before going into more complicated topics like roots and coefficients and graph of polynomial, etc., you have to remember that it's a function. You put some value in it and it gives you some output. So this idea is the basic idea, and you have to start working on problems from here. So let us see an example on how this functional view of polynomial will help us. Okay. So we'll start with the example of common roots of quadratic equations. So suppose we have two quadratic polynomials, ax square plus bx plus c and px square plus qx plus r, where a, b, c, p, q, r are complex numbers and a and p are non-zero because they are the leading coefficients. If the leading coefficients were zero, then they would not be quadratic equations. I mean, not quadratic polynomials. So you must have a and p non-zero. Suppose it is given that these two have a common root. Let us call it t. What can you say about t? So without thinking too much, just substitute t into the polynomials and equate it to zero. This is basically where we are adopting the definition of polynomial is as a function. So you get two equations like this, right? At square plus bt plus c equal to 0 and pt square plus qt plus r equal to 0. So now, does anyone have any idea how we are going to solve these two equations simultaneously? I mean, have you seen this kind of equations earlier? So what is the main idea for solving these equations? I mean, forget about t square and t. Can you say how to solve equations of the form ax plus by plus c equal to 0 and px plus qy plus r equal to 0? Okay, so seems that everyone knows. So what is the name of the method? Anyone? Oh no, I'm not talking about individual equations. I'm talking about two equations simultaneously. Do you know how to solve two simultaneous linear equations? Well, these are not linear, but if you are given ax plus by plus c equal to 0 and px plus qy plus r, yes, right, that's called the cross multiplication method. So everyone knows the cross multiplication method? Well, okay. So that is basically what we are going to do here. So we are going to think of these as linear equations by replacing t square by x and t by y and see what we get out of it. So you have these two simultaneous linear equations, and as you know, they are going to be solved using cross multiplication method. You have to be careful that this x and y are t square and t, but that doesn't change the method at all. It's the same method, exactly the same. And have you done the derivation of the cross multiplication method? Okay, so maybe you have just solved those equations by hand and shown that the answer you get out of cross multiplication is the same. But just for your knowledge, an even more general form of the cross multiplication holds, and you will learn that in matrix algebra if you take up science in future. I mean, it's a very useful thing, at least just for solving the equations. Well, theoretically maybe not that useful, but practically for the sake of solving equations, it's a very useful thing. It's called Cramer's rule. It's a much more general method, and the basic idea of Cramer's rule is that you express these equations in matrix form, and you express the right hand side as a column vector, and you basically replace the individual columns of the left hand side with the right hand side and divide by the determinant. So if you are interested, you might search up on Google or you might ask me personally. I will give you some more information on it. So that aside, we are going to solve these two equations simultaneously. So let's see. So can you follow how this came? T square by BR minus QC equal to T by PC minus AR equal to 1 by AQ minus BP. Are you sure you follow it? Write in the chat, please, if anyone doesn't follow that, how we came to this equation from the previous one. Okay, so you follow it, right? So basically, now you have the expressions for T square and T. T square comes out to be BR minus QC by AQ minus BP, and T comes out to be PC minus AR by AQ minus BP. So before I proceed, I want to know from all of you, when does this method become invalid? Like if BR minus QC equal to 0 or PC minus AR equal to 0, does this expression become invalid? This cross multiplication method become invalid? Okay, so you have done the derivation, or at least you have read about it. When will the cross multiplication method become invalid? Okay, so if you don't know, let me tell you, although it is true that in this case, we are seemingly dividing by BR minus QC and PC minus AR, no, you are not exactly correct. Even if BR minus QC and PC minus AR are equal to 0, observe that this final expression doesn't change. I mean, BR minus QC equal to 0, then simply in the next equation T will be equal to 0, right? Or PC minus AR equal to 0, T will be equal to 0. So in general, we go back to the previous page. So we are doing the cross multiplication method. In general, in these equations, if BR minus QC is 0 or PC minus AR is equal to 0, the method does not become invalid. The thing that we are doing in this case, when we are seemingly dividing by BR minus QC and PC minus AR, mind this is just a notation. This is not actually division. This is just a notation meant to, help you remember the expression. This expression doesn't mean division. The only way in which this method becomes invalid is when AQ minus BP equal to 0. In that case, this final expressions will also become invalid. I mean, there is division by 0, and you can't do that. So the reason for this is basically from matrix algebra. That is, if you have the determinant of the matrix to be 0, then you will not be able to solve these two equations simultaneously. If the determinant is not 0, then you will be able to solve the equation simultaneously. The determinant is 0, then many complications will arise. Like, for example, there might be no solution, there might be infinitely many solutions, and so cross multiplication method is not meant for that. Only when the determinant is non-zero, the cross multiplication works. And in terms of the coefficients, all it means is only AQ minus BP has to be non-zero. Okay, so everyone got it? Okay. So now the remaining steps are very simple. T square equal to BR minus QC by AQ minus BP, and T equal to PC minus AR by AQ minus BP, where AQ minus BP is non-zero. So now you just substitute the value of T inside the T square. So what you will get is PC minus AR by AQ minus BP whole square equal to BR minus QC by AQ minus BP. And then you just multiply AQ minus BP both sides, and you will get this final expression, that is PC minus AR whole square equal to BR minus QC into AQ minus BP. So this is the condition for the two equations to hold simultaneously. This is precisely the condition for the two quadratic equations to have a common root. So we call this kind of a condition a necessary condition. Necessary means if that has to be true, then this has to be true. But my question to you now is, is it also a sufficient condition? That is, if this is true, then is it necessary that if this is true, then does it follow that those two equations have a common root? So what do you think? Should it be a sufficient condition? Like just think about reversing the steps. I mean, how can you reverse the steps? Like from BC minus AR square equal to BR minus QC into AQ minus BP. How can you get this AT square plus BT plus C equal to 0 and PT square plus QT plus R equal to 0?
Wait, wait, can you show the previous slide once? Just
Yeah, okay. I'm showing the previous slide. Yes. Please raise your volume a little bit. I'm not audible.
wait, how did a common t square appear in both equations? Like if the equation, if the quadratic equation is ax square plus bx plus c, then if we substitute alpha and beta into both equations, won't there be two different terms with squares in them? Like one would be a alpha square plus b alpha plus c, and the second one would be b alpha. Oh wait, never mind. I misunderstood.
Yeah. It's not one equation. We are solving.
We are doing two equations with common roots.
Yeah, we are solving two equations simultaneously. Okay, so one of you is saying that another condition can be that PC minus AR is not equal to 0. Okay, so let's discuss this situation. Suppose you are given only PC minus AR square equal to BR minus QC times AQ minus BP, and suppose PC minus AR is equal to 0. Then what will happen? So this equation is given, and suppose it happens that PC minus AR is equal to 0. Then what do you get?
If PC minus AR is equal to 0, so then we get either BR equals QC or AQ equals BP.
So you get BR equal to QC and AQ equal to BP. So you basically have three equations now. PC equal to AR, BR equal to QC, and AQ equal to BP, right? So let's go back to the previous slide. What happens then? So two simultaneous. If you are replying, please reply in to everyone, not privately. I'll copy the text and paste it and reply to everyone. Okay, so basically there are two problems that are arising here. One of you is saying that if PC minus AR equal to 0, then what will happen? Because we derived it assuming that PC minus AR is was it PC minus AR by the way? Oh well, let me see it once again. Not PC minus AR, it was AQ minus BP, I think. Yeah. So if AQ minus BP is 0, then this derivation goes wrong. Not PC minus AR. Okay. So if AQ minus BP is equal to 0, then there is a problem with this derivation, and we are not sure if the other way uh, works or not. If indeed you have two simultaneous, just like two pair lines can have a unique intersection point, but one point of intersection doesn't imply a unique pair of lines. Well, okay, you are thinking in terms of linear equation, that is okay. But suppose let us go back to the equation. Suppose that condition is not there, that is that aq minus bp is not zero there, and our derivation so long has been fine. These denominators are not zero. Suppose we are given this condition, that is pc minus ar whole square equal to br minus qc into aq minus bp. So from here you can conclude by dividing by aq minus bp that PC minus AR by AQ minus BP whole square equal to BR minus QC divided by AQ minus BP, right? Can you divide both sides by AQ minus BP whole square, because we have assumed that AQ minus BP whole square is not zero. So you get back the previous step, that is PC minus AR by AQ minus BP whole square equal to PR minus QC by AQ minus BP. So now if I substitute, forget about t, let us substitute t naught equal to pc minus ar by aq minus bp. I am writing in the chat, please follow. T naught equal to pc minus ar by aq minus bp. And what do you get? You get two things, right? T naught is given like that, and then you have br minus qc by aq minus bp will be equal to t naught square, right? Okay. So now if you substitute, okay, that's correct. So if you substitute back into these equations, are they satisfied? I mean, you should have a pen and paper at hand, otherwise it will be difficult. Substitute back those values, that value t naught, into these equations. Are these equations satisfied? So you just have to back substitute. There's nothing to think much about it. Okay. So substitute back, and one of you tell me if those equations, if the equation is satisfied or not. The equations are satisfied, right? So basically, if you are given, if you are given that that AQ minus BP is non-zero, then actually it does follow that those equations will be satisfied. So that is the only thing which is hindering us from doing anything. That AQ minus BP is zero case. So basically, this expression is rather powerful for us. So now what will happen if AQ minus BP is equal to zero? If AQ minus BP is equal to zero, then what do you think will happen? Then where will we go wrong? We will go wrong mainly in the division part. We cannot divide by AQ minus BP whole square either. But what will happen if AQ minus BP equal to zero? Does this tell you anything about the quadratic equation? So suppose you have AQ minus BP equal to 0, and since those equations are quadratic, you know that A is non-zero and P is non-zero. So you are given two things right now. AQ minus BP equal to 0, and that condition PC minus AR whole square equal to AQ minus BP times BR minus QC. So if AQ minus BP equal to 0 and PC minus AR equal to 0, that is PC equal to AR, then what happens? What do you mean by quadratic equation will be is PC minus AR will be equal to 0? So no, I did not understand what is meant by quadratic equation will be 0 or not. The quadratic equations are given to you right now. So now you are given that AQ minus BP equal to 0. Does that imply that ER equal to QC? So how did you arrive at that? But I'm not sure how you arrived at BR equal to QC. It might be true, I don't know. So okay, so at least we have that AQ equal to BP and PC equal to AR. So what will be the effect on the quadratic equations? I'll let you think for a while and can reply to me after some time. Or you might unmute yourself also right now. This is a bit difficult to write down in the chat, so you can unmute and speak. If PC equal to AR and EB equal to AQ and dividing, you get C by B. Okay, you are dividing C by B equal to R by Q. E by B equal to R by Q. So CQ equal to BR. Okay, so that's how you got it. But are you sure you can divide by divide PC by BP and AR by AQ? So, okay, if BP is equal to 0, then you are given that P is non-zero. So in that case, you will have B equal to 0. If B equal to 0, then automatically Q becomes equal to 0. So CQ equal to PR again. Okay, so that's right. So if I'm writing in the chat, if B non-zero and Q non-zero, then you can divide. Then you can divide and arrive at the thing that we got right now. If any one of them is 0, say B is equal to 0. If B equal to 0, then AQ equal to 0. But A is non-zero, so Q equal to 0. So if you get Q equal to 0, then do you get back this equation? CQ equal to BR? That equation will hold because both sides will become equal to 0 in this case. So right now you have three very nice conditions with you. You have got PC minus AR equal to 0, that is PC equal to AR. You have AQ equal to BP and BR equal to QC. So now from these three equations, what can you conclude? I mean, this is a lot of information for you. What can you conclude from these three equations about the two original quadratic equations, AT square plus BT plus C equal to 0 and PT square plus QT plus R equal to 0? What do you conclude? So I'll give you a hint. Let us first consider the case when none of the coefficients is zero. I mean, let us forget about that case for now. In very degenerate case, we can deal with it later. Assume I'm writing in the chat, none of the coefficients is zero. What do you conclude from those three equations? That is PC equal to AR, AQ equal to BP, and PR equal to QC. If none of them is zero, then you can basically divide by anything you want. Okay, so I'm going to give you the answer. Basically, what you get from the first equation is A by P equal to R by C. Sorry, A by P equal to C by R. And from the third equation, you get C by R equal to B by Q. So basically, what you get is A by P equal to B by Q equal to C by R. So if you let all of these quantities to be equal to some K, equal to K, suppose, then you get A equal to Pk, P equal to Qk, and C equal to Rk. So what you get is that quadratic equation, first polynomial equal to K times the second polynomial. K times the second polynomial. So does this tell you anything about the roots of the polynomials? So assume that these equations are all over complex numbers. So you will always have roots. I mean, there is no question of not having a root right now, because these are all quadratic equations. They will have two roots, might be repeated, but there will be roots. Complex numbers might be there. So what can you say about the roots from this equation? This first polynomial equal to k times the second polynomial. They will have same roots. The thing is, if the second polynomial is zero, then automatically the first polynomial becomes zero. If the first polynomial becomes zero, then two things are possible: either k equal to zero or the second polynomial is zero. But can k be equal to zero? I don't think so, because a by p, I have let a by p equal to k. So if k equal to zero, then a equal to zero, and that's a contradiction. So k is not zero. So if the first polynomial is zero, again the second polynomial is zero. So this means that not only do they have one common root, all of their roots are common. So at least in the case when all the coefficients are non-zero, then that equation is sufficient to guarantee you common roots. Even if this AQ minus BP is equal to zero, automatically that equation will get adjusted some to make the roots common. So if one of the coefficients is zero, let us say b equal to zero, or r equal to zero, or c equal to zero, 2 equal to zero, again you will have some degenerate cases. Now, since I don't have much time now, I will leave it to you to think what happens when any one of the coefficients is zero. You will get some degenerate thing, and I hope you will get common roots also. So far now, so far, have you understood everything? Discuss the degenerate case of zero coefficients among yourselves. I mean, there's nothing to do right now. I mean, nothing else left to do. Almost everything is done. You can discuss on the WhatsApp group and can tell me the answer later on. So let's move on to the next topic. Okay, where are the so we will recall some of the concepts that you learned in the previous class. That is, we will start from fundamental theorem of algebra. So if I have a non-constant polynomial p over complex numbers, then it must have a root. When I say root, it means that it's some value alpha such that p of alpha is 0. Now, since we are viewing over complex numbers, you can have a complex root. You can have imaginary roots. It's not necessary to have real roots, okay? But you will always have a root as long as it's a non-constant polynomial. If it's a constant polynomial, two things are possible. Either it is identically 0, in which case every number is its root, or it's a non-zero constant, in which case it doesn't have any. So those are boring cases and we don't deal with. So we will rejoin after some time. So I'll just quickly go over this thing. So the fundamental theorem of algebra is anything but fundamental. Its proofs requires concepts beyond the scope of this lecture. You will need something like complex analysis or topology in order to prove the fundamental theorem of algebra, and we won't be discussing here. But you will require this fundamental theorem of algebra everywhere in mathematics, just as long as you are doing algebra. So after this, we will prove this theorem. Every polynomial of degree n over complex numbers has exactly n roots counted with repetitions. But since the class is going to end in 5 minutes, I think we will stop here and let you rejoin. Okay? No, it's not. Every polynomial of degree n over complex numbers has exactly n roots counted with repetitions. So how do we prove this? So all of you are familiar with division algorithm over complex numbers, right? I think it was discussed in the previous class. Everyone familiar with division algorithm, or at least with factor theorem or something like remainder theorem? Okay, so let alpha be a root of f. So I am dividing f by x minus alpha. So by division algorithm over complex numbers, I get f of x equal to x minus alpha times g of x plus c, where g is the quotient and c is a constant polynomial. So why do I have a constant polynomial here? Because the degree of the divisor is 1. So either it will exactly divide f, in which case the constant will be 0. But if it doesn't divide f, it will leave a remainder whose degree will be less than the degree of the divisor. But the degree of the divisor is 1. So the degree of the remainder must be 0. And hence c is the constant polynomial. So in this one, in order to get rid of this x minus alpha times g of x, I will substitute x equal to alpha. So I get c equal to f of alpha equal to 0. And from there, you get f of x equal to x minus alpha times g of x. So if the degree of f is n, then the degree of g has to be n minus 1, right? Because you are multiplying x with the highest power of x in g. So then you get the highest power of x in f. And the highest power of x in f will be x power n. So the highest power of x in g has to be x power n minus 1. So now basically we will give an inductive argument. So base case is very easy to prove. So if you have a polynomial of degree 1, you know it has exactly one root. Is it correct? You have a polynomial of degree 1, then do you have exactly one root? Then px plus q equal to 0. And since it's of degree 1, p is non-zero. So exactly one root will be there, x equal to minus q divided by p. X equal to minus q divided by p. So our base case of induction is true. Base case is say n equal to 1. So now let us assume that for k lesser than equal to n minus 1, every polynomial of degree n over complex numbers has exactly n roots, counted with repetitions. So that means g, which is a polynomial of degree n minus 1, has exactly n roots. But then f has exactly, every polynomial of degree n minus 1 has exactly n minus 1 roots. So g has exactly n minus 1 roots. So how many roots will f have? Then f of x will be 0 if and only if x minus alpha times g of x will be equal to 0. That is true if and only if x minus alpha equal to 0 or g equal to 0, g of x equal to 0. Now, counted with repetitions, he has exactly n minus 1 roots and x minus alpha has exactly 1 root. So that gives you a total of n roots for f, correct? Okay. So that basically is the induction hypothesis, and it is true. So whenever it is true for n minus 1, it is true for n. And hence you get by induction that every polynomial of degree n over complex numbers has exactly n roots counted with repetitions. Now, by repetitions, I mean when you factorize f in terms of its roots, you might get square power or cubic power and so on. So this thing is important. Otherwise, you can say that at most n distinct roots will be there. So next, we will get a nice factorization. I hope you have seen it earlier. F of x equal to x minus alpha times g of x. Now you can do the same thing to g. So if g is the constant polynomial, you cannot go any further. But if g is a non-constant polynomial, you can get another root, say beta. And then you can write g as x minus beta times h of x. And then if h is the constant polynomial, you end the thing there. Otherwise, it will have another root, say gamma. And you write h as x minus gamma times, say r of x. And you keep on going unless and until you get a constant polynomial. So in that case, you will get a factorization of the form, say x minus alpha times x minus beta times x minus gamma and so on up to something x minus k or something into some constant c. So now, just for notational convenience, we will write this as x minus alpha 1 times x minus alpha 2 and so on up to x minus alpha n into some constant where alpha 1, alpha 2 and so on up to alpha n are the roots of f. Now, this constant c will be equal to the leading coefficient an. Can you tell why? Why will the constant be equal to an? So f of x is some an x power n plus an minus 1 x power n minus 1 and so on up to a naught, and on the right hand side you have equal to c times x minus alpha 1 times x minus alpha 2 and so on up to x minus alpha n. So what do you do after this? Like why will an be equal to c? Since leading coefficient has one as the leading coefficient of x minus alpha 1 times x minus alpha 2 and so on up to x minus alpha n is 1. The leading coefficient of the right hand side will be n. Sorry, leading coefficient of the right hand side will be c, and the leading coefficient on the left hand side will be n. So you can equate the coefficients over when you are viewing over complex numbers, and that's why c will be equal to n. And not only that, you will get individually all the coefficients to be equal. Now, why that is true, that one you have to think a little bit. So I'll let you think on your own that why this equating the coefficients works. Is suppose that the polynomial is n and so on up to plus c. We can take c common and factorize in terms of roots. Then c is a the constant will get multiplied with the leading coefficient. No, wait, I didn't get you. I mean, what are you saying? Suppose that the polynomial is, how did a n and a power n? What is a power? Constant will get multiplied with. Assuming a general polynomial. So you can unmute yourself and speak. I mean, it's difficult to write right.
I'm saying that suppose we take a general polynomial and then take the constant term common, that's a naught into x equals to that term common, and then we can write this in terms of the factors. This product of, we can write this as x minus alpha 1 dot x minus alpha 1, that part. So that becomes a leading quotient automatically, the constant time.
Okay, I have to say that your audio is not too good, so I cannot hear you properly. Write down the whole thing in the chat. I will wait. Your audio is not that good. So write it down in the chat. Okay, so I'll proceed. So basically the idea is, okay, you'll mention later in the group. So I am not revealing the reason right now. It's very simple. The thing that you have to do is basically you have to take some values like x equal to 0 and so on and continue with that. Okay. So it's simple, and I don't think I need to help you on that. So on the basis of this factorization, let's have an exercise. This exercise is also there in the PDF that I sent. Let u, v, w, and t be the roots of the equation x power 4 plus px cube plus qx square plus rx plus s equal to 0. There will be 4 roots, might not be distinct, might be repetitions, but there will be 4 roots. So 4 complex roots are there. So what I want you to do is I want you to find 1 plus u square times 1 plus v square times 1 plus w square times 1 plus t square. So what is one approach that immediately comes to mind? Since we're dealing with roots and you want to express it in terms of coefficients, you want to use Vieta's relations, right? But the problem is, you're expanding using Vieta's relationship is very complicated. I mean, there will be many terms coming up. So using Vieta's relationship is not a very ideal thing to do in this situation. Rather, we will use a much smarter method. Basically, what we will do is we will take an example. What will happen if suppose you have 1 minus u square instead of 1 plus u square? What happens if 1 minus u square is given in place of 1 plus u square? Can you factorize 1 minus u square somehow? Yes. So basically, we are going to factorize. If you factorize, what you will get is you will get something very easy. That thing x power 4 plus px cube plus qx square plus rx plus s. That thing will be equal to x minus u times x minus v times x minus w times x minus t. So now to get 1 minus u square, you will just have to substitute 1 and minus 1 there. There will be an extra minus sign which will be cancelled anyways. So you will get some nice expression. So you have to do something similar to that even for 1 plus u square. So 1 plus u square, you have to write this thing as equal to
X square minus I square.
yes, exactly, using iota. You have to, yeah, I mean, don't call it I, it's called iota. Okay, so it's a Greek letter, it's not the English I, so I'll prefer calling it iota. So when you write it as 1 plus u square equal to 1 minus iota minus u times iota plus u, well, no, that is not exactly correct. You will have another minus sign there. So writing in the chat 1 plus u square equal to minus times iota minus u times iota plus u. So now all you have to do is you have to substitute iota in this equation. So iota iota minus u times iota plus u into another minus 1, that thing can be written as iota minus u into minus iota minus u. So now we have to substitute iota and minus iota in that factorization, and then you will easily get this kind of a expression. You will get very nice expressions in when you substitute iota and minus iota inside this x power 4 plus bx cube plus qx square plus rx plus s, and you will get back this expression. And this method is very useful, like when you cannot do using 1 plus u square, or let's say a square plus b square, you do using 1 minus u square or a square minus b square, and then you get some motivation out of it. Then you use complex numbers or roots of unity or something like that in order to get a very nice expression. So this method is useful. So we'll go over to the next slide. The fact that a polynomial of degree n has at most n distinct roots. Now, at most n distinct roots because there are n roots with repetitions. So if there are say k distinct roots, then with repetitions there will be some, let's say, k plus l roots, and that k plus l is equal to n. So k is at most equal to n. So a polynomial of degree n has at most n distinct roots, and this fact is very useful in proving that a certain polynomial is identically equal to 0. So how do we prove it? We will prove by contradiction. Suppose the polynomial is non-zero. Non-zero polynomial has a well-defined degree. At least over complex numbers, it has a well-defined degree. Let's call the degree n, where n is a natural number. So you have to show that there are at least n plus 1 distinct roots and arrive at a contradiction. So that is a general strategy. You assume that the polynomial is non-zero. If it is non-zero, assume it has a degree n, and you find n plus 1 distinct roots for that polynomial, and then this will imply in turn that that polynomial must be 0. Otherwise, this might not have been possible, and this will give us a contradiction. So everyone follows this argument. Okay, so right now let us see an example based on this. So we have a polynomial x minus a times x minus b divided by c minus a times c minus b plus x minus b times x minus c divided by a minus b times a minus c plus x minus c times x minus a divided by b minus c times b minus a. And that we have to prove is equal to 1 when a, b and c are distinct complex numbers. I mean it does not depend on x. So one approach might be, you might try to expand the whole thing. You might try to evaluate the entire product, and you will obviously get equal to 1, but that is not a very smart method. I mean, for this 3 variables, it is still easy to multiply out, but when you will have 4 5 variables, that time it will be next to impossible. So in that case, you have to do what is a cyclic expression, so we can substitute x as ab. Yeah, you have to substitute. That's exactly what we are going to do. So on left hand side we have one polynomial, on right hand side we have another polynomial. So let us consider a new polynomial, this summation over x minus I by x minus times x minus b by c minus a times c minus b minus 1. So in order to prove that this is 0, by the method we discussed earlier, we have to consider the degree first. So if it is non-zero, then its degree is at most 2, because by multiplying x minus a and x minus b and so on, you can at most get x squared term, nothing more. But observe that if you substitute a in this expression, you get 0, because the first and the third terms are 0 and the second term is 1. So it cancels off the last one, and so the entire thing is 0. Similarly, if you substitute b, then the first and second terms are 0 and the third term is 1. If you substitute c, then the second and third terms are 0 and the first term is 1. So you will have 3 distinct roots for this polynomial, although it has degree at most 2. And this gives us a contradiction. It cannot be non-zero polynomial. It has to be the 0 polynomial. So if this polynomial is 0, then that polynomial, this x minus a times x minus b by c minus a times c minus b plus all this, is equal to 1. for all values of x in complex numbers. So everyone convinced with this argument?
Can you
You are free to speak.
can you repeat once?
Okay, so the argument is we consider a new polynomial. This polynomial on the left hand side minus 1. So we are trying to prove that it is equal to 0. Equal to 0 for all values of x in complex numbers. So we are trying to prove this by contradiction. Let us assume that this is a non-zero polynomial. If it has a non-zero polynomial, it has a degree n. But what degree can you get out of this polynomial? By multiplying x minus a and x minus b and then x minus b and x minus c, you can get degree at most 2. I mean, there might be cancellations later on because there might be some plus or minus and they might get cancelled. But degree can be at most 2. You might get degree either 0 or 1 or 2, right? Like, who is asking this? I mean, I need you to reply.
Understand. Understand.
Okay, so
Okay, so we understood.
okay, so basically, so that is how it is. You find out degrees at most 2 and you have 3 distinct roots. So it cannot be a non-zero polynomial. So this is a very interesting argument. Whenever you have a polynomial expression, I mean polynomial identity rather, you want to prove a polynomial identity, and evaluating the polynomial identity by hand is very difficult. So you do a smarter move, that is you predict the degree of the polynomial if it is non-zero, and then you find some other roots. So sometimes you will see that often there are some polynomials for which it is easier to prove that the equation holds for all integers, but it is difficult to prove for all real numbers or for all complex numbers. But the interesting fact is that if it is true for all integers, then it will be true for all complex numbers, because then the polynomial will have infinitely many distinct roots. If the polynomial has infinitely many distinct integer roots, then it has infinitely many distinct roots. So the only polynomial which can have infinitely many distinct roots is the identically zero polynomial, identically zero over all complex numbers. So you might try to prove it for integers first by using some combinatorial or number theoretical argument, and then you can extend it to arbitrary numbers, rational numbers, real numbers, complex numbers, I mean, whatever you move on. The next slide. So before I discuss this, I think we will need more classes for this slide. Okay, anyways, we will complete as much as we can in 1 more hour. So another way of stating the idea just now is that if two polynomials of degree at most n agree at n plus 1 distinct points, then they must be equal. Because if you consider the difference of the two polynomials, let us say px minus qx, then the difference also has degree at most n. But if p and q give the same value at n plus 1 distinct points, that means p of x minus q of x has n plus 1 distinct roots, but it has degree at most n, and hence must be the identically zero polynomial. That is, p of x has to be equal to p of x for all x. So this idea is pretty useful sometimes. At what? There is a large square block on your screen. I cannot see any.
It's fixed now.
Now we can see.
Now it's gone, right? Yeah. Well, okay. Actually, this. Yeah, there is some visibility. I mean, it's a bit slow. The when I change the slide, it takes some time to change it on your screen, so it stays for some time there. I have cleared all the annotations. Don't worry. So what I was saying was, if P and Q are two polynomials of degree at most n, whose values at n plus 1 distinct points are equal, if you consider P of x minus Q of x, then its degree is also at most n. But since P of x is equal to P of x for n plus 1 distinct value of x, it means that P minus Q has n plus 1 distinct roots at least. Then by our previous argument, P minus Q has to be the identically zero polynomial. That is, P of x has to be identically equal to Q of x. Now this idea is very useful sometimes. Suppose you are given an unknown or very complicated polynomial p whose degree is given to be at most n, and you know its values at n plus 1 distinct points. Now we don't want to deal with complicated expressions. So what we try doing is we try guessing another simpler polynomial of degree at most n which has the same values at those points. Then by this argument that we gave just now, those two polynomials will be equal. Like for example, you will see a problem in one of in the PDF, something like p of 0 equal to 2020, p of 1 equal to 2019 or something like that. In that one, this p is an unknown polynomial, but you know its values at many points, right? So what you try doing is you try guessing another polynomial p, another polynomial, let's say q, whose values at those points are the same. So if you have two polynomials p and q of degree at most n, whose values at n plus 1 distinct points is the same, then those two polynomials must be equal. Now this always simplifies our work because then you don't have to deal with the complicated or unknown polynomial anymore. You can deal with the simpler one. Now this special kind of polynomial has a name. It is called the Lagrange polynomial. What is the Lagrange polynomial? It is a unique polynomial of degree at most n passing through the given n plus 1 distinct data points. So suppose you have say n equal to 2 and you are given that the polynomial gives the polynomial is f and f of 1 is equal to say 2, f of 2 is equal to say 3 and f of 3 is equal to say 4. So you know the value of the polynomial at 3 distinct points, whereas the degree of the polynomial is 2 or maybe at most 2 also, doesn't matter. So can you guess one polynomial, one such polynomial such that f of 1 is equal to 2, f of 2 is equal to 3 and f of 3 is equal to 4? Write it in the chat. Yeah, so x plus 1. So what our argument shows is that what someone is requesting to annotate the shared content. Like, what do you want to annotate? Did you? Oh, okay. So my mistake. So yeah, so you guessed it right. You have a polynomial x plus 1, value at 1 is 2, value at 2 is 3, and value of 3 is 4. So suppose you have another polynomial g, which I don't tell you, unknown polynomial. All I am telling you is the degree of the polynomial is at most 2, and its value at 1 is 2, value at 2 is 3, and value at 3 is 4. Then by the argument I gave just now, what can you conclude? So the question is, guessed that one such polynomial for which the value at 1 is 2, value at 2 is 3, and value at 3 is 4, one such polynomial is x plus 1. If one such polynomial is x plus 1, and then you have another polynomial g whose degree is at most 2, but its value at 1 is 2, value at 2 is 3, and value at 3 is 4, then what can you say about g? No, the degree there has to be at most 2. So that polynomial doesn't work. That x minus 1 times x minus 2 times x minus 3 and so on. So degree is given to be at most 2. So what can you conclude about g by the argument I gave just? Keep in mind that one such polynomial not necessarily equal. Yeah, they are the same polynomials. Because if you consider the difference g minus x plus 1 minus within brackets x plus 1, then that thing has degree at most 2, but its value at 1, 2, and 3 is 0, right? So it has 3 distinct roots. So it cannot have. So it cannot be a non-zero polynomial because a non-zero polynomial of degree at most 2 can have at most 2 distinct roots. It must be the identically zero polynomial. P of x is equal to x plus 1 for all real x. The interesting thing is that we had to check it for only 3 values. So this polynomial, this x plus 1, is called the Lagrange polynomial with respect to these data points. By data points, I mean these points 1, 2, 2, 3, and 3, 4. P is the, or let's say x plus 1 is the Lagrange polynomial with respect to these data points. And this polynomial is always unique. So whenever you find in any question given that a polynomial g with these 3 data points, the degree at most, you can easily say that this is equal to x plus 1. And that's why it has a very special name. So now, instead of giving 1, 2, and 3 and 4, if I give you some alpha 1, alpha 2, and so on, can you find out this Lagrange polynomial? So let me write it in the chat. So let's say we have polynomial of degree, or let's say we have n data points, or let's say n plus 1 distinct data points, as we have said till now, alpha 1 comma beta 1, then alpha 2 comma beta 2, and so on up to alpha n plus 1 comma beta n plus 1, and degree n, then that polynomial will be equal to the Lagrange polynomial by our previous argument. But can you guess this polynomial in terms of alpha 1, beta 1, alpha 2, beta 2, and so on? Can you guess this polynomial? I will give you a hint. It is very similar to the polynomial that we saw just in one of the previous slides, that is x minus a times x minus b, something similar to that. You can unmute yourself and speak if writing down the expression is difficult.
Dada, will I?
Yes, unmute yourself.
Yes, Dada. Dada, can the polynomial be x minus alpha 1 plus beta 1 into x minus alpha 2 plus beta 2 dot till x minus alpha n plus 1 plus beta n plus 1?
So if you substitute x equal to alpha 1 there, does it give you beta 1? I'm not sure if this is correct. Maybe the thing that I am guessing is equal to your answer, but we make all rest terms 0 and only one term will take the value of beta 2, means all the rest will have a factor of x minus alpha 1. Not beta 2, it will be beta 1, right? Yeah, beta 1 will be there from beta 2. Yeah, so yeah, all the rest terms will have a factor of x minus alpha 1. So now you have a little bit of lead on this problem. So there will be a factor of x minus alpha 1, but what will be the first term that you are talking about, the one which does not have a factor of x minus alpha 1? What will be that term? Okay, you might unmute yourself if you have raised your hand. Unmute yourself and speak, or write in the chat whatever you want. So did you raise your hand by mistake or something? I mean, I'm not sure if you... Okay, I assume you raised it by mistake. So I'll tell you the answer now. So basically it has to be something like this. So instead of thinking about this beta 1, beta 2, and so on, let us first think about a very simple case. Let us assume that at alpha 1 it gives you 1, and at all other remaining points it gives you 0. Then what will be the polynomial? What do you think should be the polynomial? So I'm telling you the answer. So basically, since at all other alpha is beta 1 times, yeah, that is correct. So basically, there is something wrong with this. Yeah, correct. So it's correct. So summation over all possible values, right? Yeah, you have to sum it over. Like this one you wrote only for alpha 1 and beta 1. So basically, what he has said is correct. So what this polynomial, what Sahil has said is that you have x minus alpha 2 times x minus alpha 3 and so on up to x minus alpha n, and then you divide the whole thing by, what have you written? So you divide the whole thing by alpha 1 minus alpha 2 into alpha 1 minus alpha 3 and so on up to alpha 1 minus alpha n, and then you multiply by beta 1. So what this polynomial gives you is at alpha 1 it gives you beta 1, and all other alphas it gives you 0. So now, in order to get the answer for the general case, what you need to do is you need to sum it over all possible other alphas. That is, next term will be say beta 2 into x minus alpha 1 times x minus alpha 3 and so on up to x minus alpha n divided by beta 2 minus beta 1 times beta 2 minus beta 3 and so on up to beta 2 minus beta n and so on. That is the correct answer. I mean, uh, right now, if you have not understood fully, it is okay. If I find some time, I will show you the Lagrange polynomial in another slide. It is written down, but I don't want to go over to that slide right now. Or I will write it over WhatsApp, or you might discuss over WhatsApp. What he has said is correct. So basically, all you have to know right now is it is possible to guess the polynomial. So can you realize that how powerful this concept is? All you are given about a polynomial is it has degree at most 10 and n plus 1 distinct data points are given. Now, using only this much information, you can exactly evaluate the polynomial, because that polynomial g minus this polynomial which Sahil has said, that this difference has got n plus 1 distinct roots, whereas the degree is at most 10. So it must be identically equal to 0. That means g has to be exactly equal to that polynomial. So this is a very interesting concept. So, did you understand this? Did you understand what the polynomial which Sahil has written down in the chat? No, I mean, I'm asking. Yeah, I was asking you. So, okay, I will show you another slide. Just wait for a minute. I have to move over to that slide in order to show you. So, let's see. I have to skip quite a lot of slides. That's why I didn't want to discuss it right now. So, anyways, I will show you. Okay, so now can you all see this screen? It says Lagrange interpolation.
Yes.
Yeah, okay. So basically, now this first statement is something like f be an arbitrary field. Now I haven't told you what a field is. Right now you can just take f to be the set of complex numbers or real numbers or rational numbers. So basically, field is a special type of algebraic structure which has some operations defined on it, operations of addition and multiplication. You will learn about fields not in you will not learn about fields in school. You will learn about it in college if you take up maths or you take up science. So right now, the fields that you have seen are say real numbers, complex numbers, and rational numbers. Integers do not form a field. So most of the sets that you have seen form a field. In the real numbers, rational numbers, complex numbers are very nice sets, they form fields. Integers do not. So you can think of this as real numbers or complex numbers or rational numbers. I am dealing with complex numbers only. So you have n distinct scalars, C1, C2, and so on up to Cn. And then you can find a polynomial, let's say f of x, which is equal to x minus C1 times x minus C2 up to x minus Cn, which evaluates to 0 at each of those n scalars. Now I want to extend this idea. Suppose I want a polynomial which gives 1 for C1 and 0 for all other scalars. So I was talking about alpha is now just, I've changed the notation a bit, now it is Ci. So I want 1 at C1 and 0 at other scalars. Since we want all the other scalars to be roots, this polynomial is a possible candidate. This x minus C2 into x minus C3 up to x minus C. There might be many other polynomials, but this is a possible candidate. But there is a problem with this polynomial. If you substitute C1, you don't get 1. You get C1 minus C2 times C1 minus C3 and so on up to C1 minus C. So in order to get 1 at C1, what we will do is we will divide this expression, this x minus C2 into x minus C3 and so on, by C1 minus C2 into C1 minus C3 and so on. So you get this product from I equal to 2 to n, x minus Ci by C1 minus Ci. So now do you follow that at C1 it gives you 1 and at C2, C3 and so on up to Cn it gives you 0? Do you follow?
Yes.
Oh, why? Could you give the reason? I don't think I understand.
Okay, so did you understand the first polynomial that we discussed, this x minus C1 into x minus C2 and up to x minus Cn? That it gives you. So this first thing that we discussed, that is if we want 0 at each of the scalars, that is if we want 0 at C1, 0 at C2. Huh? Okay, so pi is just a product notation. Like, okay, so I will just tell you what pi means. Pi means that product notation, product over x minus Ci by C1 minus Ci. It means, I'm writing down in the chat, it means x minus C1, sorry, x minus C2 times C1 minus C2 into x minus C3 times C1 minus C3 into x minus C4. Well, I think it's division by, wait a little bit, I will write down in the chat. So basically pi is this expression. So it's just like summation notation. Summation over I equal to 2 to n, most of you know, I think. On product means this, that is product over I equal to 2 to n, x minus Ci divided by C1 minus Ci. This thing means x minus C2 by C1 minus C2 into x minus C3 divided by C1 minus C3 into x minus C4 divided by C1 minus C4 and so on. So do you, so now do you understand the pi notation at least? I mean, everyone should reply in the chat because, okay. So, everyone please reply in the chat. Otherwise, if only one person replies, I'm not sure everyone understands. No, I am not talking about the general case. I am talking about, wait, I will go over to that thing later on. First, tell me whether you understand the notation or not. Okay, so yeah, so I think everyone understands the notation. So now I'm answering your question now that what we are dealing with. So forget about this beta 1, beta 2 and so on. Let me start from scratch. I will go over the steps one by one, like how we arrived at this idea. So suppose we have n distinct scalars, C1, C2 and so on up to Cn, and we want a polynomial which gives you 0 at each of those scalars. So can you follow that one such polynomial is x minus C1 times x minus C2 and so on up to x minus Cn? Okay, so I'll assume everyone follows this. So, and the one who asked the question first, like was confused. Are you sure you follow? Because I'm not seeing you reply. Okay, so I'll move on. So our first step was to find out a polynomial which gives 0 at all of these scalars. But that case is not that interesting because who wants only 0? We want something else too. So suppose now we want a polynomial which gives you 1 at C1 and 0 at all other scalars. So can you tell me a polynomial which gives 0 at C2, C3 and so on up to Cn? So immediately next polynomial. Yes, speak. I mean, if anyone is speaking, then go on. Okay, I will tell you the answer. So, okay, so it's better to just end the meeting here and continue in the next one because it will be difficult to just complete the whole thing in 5 minutes. So, Juanit, end the meeting right now. We'll start a new one.
Okay, okay.
So, I was saying that we want a polynomial which gives 1 at C1 and 0 at the other scalars. So first, we are concentrating on the fact that we want 0 at C2, C3 and so on up to Cn. So do you follow that one such polynomial is x minus C2 times x minus C3 to x minus Cn? I mean, are you sure? Are you following this? That polynomial which gives 0 at C2, C3 and so on up to Cn. One such polynomial is x minus C2 into x minus C3 up to x minus Cn. Okay. So everyone follows, please. Everyone please reply. Otherwise, I'm not sure everyone understands. Okay. So now we had another additional condition. We wanted 1 at C1. But if we substitute x equal to C1, what do we get? We get C1 minus C2 times C1 minus C3 and so on up to C1 minus Cn. But that might not necessarily be equal to 1. So this polynomial is not sufficient for us. What we have to do is we have to divide that polynomial by this C1 minus C2 into C1 minus C3 and so on up to C1 minus Cn. So do you follow this argument that why I am dividing this x minus C2 into x minus C3 and so on up to x minus Cn by C1 minus C2 into C1 minus C3 up to C1 minus Cn? Okay, so everyone please reply. Okay, so that is what we are doing. So this product notation, so the product notation is very similar to the summation notation. Like just imagine what would have happened if we had summation instead of product. So just replace the plus by the multiplication sign. So that thing is equal to I some product of I equal to 2 to n x minus ci by c1 minus ci. This satisfies our condition. It gives you 1 at C1 and 0 at the other scalars. So now instead of C1, let us consider a general Cj. That is, for j, we can choose a polynomial. This product over I not equal to j, x minus ci by cj minus ci, which gives 1 at cj and 0 at the other scalars. You follow this part? Okay, so most people are following. So now, if I tell you that instead of 1 at Cj, if I want beta j at Cj, what polynomial should I consider? So let us denote this polynomial which we considered 1 at Cj and 0 at other scalars by fj. So fjx gives 1 at Cj and 0 at other scalars. So what polynomial should I consider to give beta j at Cj? Exactly. So multiply fj by beta j, and then you will get beta j at Cj and 0 at the other scalars. So now think of the even more general situation. Suppose I want beta j at each Cj and not 0, rather we want beta 1 at C1 and beta 2 at C2 and so on up to beta n at Cn. So in terms of these beta j's and these fj's, what polynomial can you consider? Keep in mind that fjx gives 1 at Cj and 0 at the other scalars. So beta j fjx gives you beta j at Cj and 0 at the other scalars. So if you want beta 1 at C1, beta 2 at C2 and so on up to beta n at Cn, what polynomial should you consider in terms of these fj's? Very easy. I mean, after you say that to get beta j at Cj and 0 at the other scalars, getting the general polynomial is very easy. Just one more step. We want beta 1 at C1. Yeah, exactly. So summation over all possible values of I from 1 to n. So the polynomial which we want is a summation beta I fi. So do you follow this argument? Okay, so you and I was not aware that this. Actually, what you can do is you can drag it using the mouse pointer, or you can drag profile pictures using mouse pointer. So just drag it upward and set it to the top right corner of your screen. Because so let me type it down a little bit. So basically, he said that we want 1 at C1 and 0 at the other scalars. We consider what I'm using tab, so no mouse pointer. You can drag it using, I mean, you can touch and drag it also. There's always a replacement for mouse pointer in tabs and mobile phones also. Actually, there is an option for hiding the window view. If you hover over the profile picture. Okay, anyways, I will write down the expression. So will take some time. Fjx equal to, okay, so I don't need to write now. So someone wanted the last step again. Okay, so till how much did you understand? Like, did you understand till the Fjx? Okay, so you understood the till the Fjx. So what Fjx does is that it gives you 1 at Cj and 0 at the other scalar. Like for example, F2x will give you 1 at C2 and 0 at the other scalars. F3x, okay, you can, this meeting will be recorded, and anyways, we have to end in some time. And the remaining, I think we have to cover the remaining slides at some other lecture because it's taking some time. So
Can we do
anyways,
it on Monday then?
huh?
Monday our same time?
Yeah, okay, Monday আবার সেম টাইম, হ্যাঁ যেটা ঠিক আছে,
Okay.
সেটা ঠিক আছে। But এখন এখন কতক্ষণ আছে মিটিংটা? ওই কোনে
6:20 অবধি বোধহয় হবে।
6:20 আবার কি? এখনকার
মানে
মিটিংটা কত?
7:20 7:20।
7:20, ঠিক আছে। So I won't cover anything very complicated during this part. Okay, so you want to know how you got the last summation part? Okay, so you want the summation only. So tell me, if you want beta 1 at C1 and 0 at other scalars, what polynomial should you consider? Beta 1 F1, right? So if you want beta 2 at C2 and 0 at other scalars, so what polynomial should you consider? Beta 2 F2x. There is a subscript here. Beta 2 F2x, not Fx. Do you understand that? Okay. So now we want beta 1 at C1, beta 2 at C2, and so on up to beta n and Cn. Now, if you sum up these polynomials, this summation beta j fjx, does this polynomial satisfy the required condition? Say, does this polynomial give you beta 1 at C1? See, so only f1x will be non-zero at C1. F2x, F3x, and all other Fix. Yeah, so that's what I'm saying. Like at F2x, F3x, and so on up to Fnx will be 0 at C1. So only F1x will be there, at least at x equal to C1. So if you evaluate summation beta j fjx at C1, only beta 1 F1x will be effective there. So beta j summation beta j fj C1 will give you beta 1, correct? Okay, so now again go over to beta 2. Only f2x will give you some nice value. All other fjx will give you 0 at beta at C2. So this summation beta j fj evaluated at C2 will give you beta 2 because only the beta 2 f2x term will be there. Okay, so I want everyone to. Okay, so now you understand this argument, this summation why I considered beta j f j x. Okay, so just for completeness, I'm going to show you the, yeah, so that is, this is the entire argument. So I'm going to show you the next slide. The answer is given here. So I've used some different notations. That's why I didn't want to explain using slides. So instead of betas, I have used AJs here. So I'm sorry if you get confused with the notation a little bit. So basically, here we are considering we want A1 at C1, A2 at C2, and so on up to AN at CN. So we are considering summation j equal to 1 to an AJ FJ. So everyone understood, right? Okay. So I guess everyone got the Lagrange polynomial. Okay, so basically I did not want to discuss the explicit expression for the Lagrange polynomial here because I knew it would be complicated to show you by just by chatting. So anyways, it's good to know the things. Only thing is that we won't finish the thing. So we have to return to the previous slide. Okay, Sahil will send a PDF of the derivation. Anyways, I intended to cover it in the additional topics. So let's go back to the things that we were discussing first. So basically what I was trying to say is this idea of Lagrange polynomial is very useful. You can explicitly guess the expression for the Lagrange polynomial. So I wanted to say something more about this polynomial, but I guess I will stop here now. I will move on to the next concept, that is solving functional equations using roots of the polynomial. The roots of a polynomial can give us a surprisingly large amount of information on the polynomial. So suppose we have a functional equation f of x square plus f of x times f of x plus 1 equal to 0 for all x in complex numbers. And we want to find all polynomials f over complex numbers which satisfy this functional equation. I wanted to discuss this solution here, but I think I will cover a few more topics I want to cover. That's why I won't discuss the solution, but I will give you the hint here. That is, if you substitute alpha in this equation where alpha is a root of f, then observe that this second term f of alpha times f of alpha 1 becomes 0. Then f of alpha square is also 0, which means that alpha square is also a root. So now in the original equation, again if you substitute alpha square, then f of alpha square times f of alpha square plus 1 becomes 0. Then f of alpha square whole square becomes 0. That is f of alpha power 4 becomes 0. So in this way you keep continuing. Alpha, alpha square, alpha power 4, alpha power 8 and so on. This gives you infinitely many zeros. Now the idea is if the magnitude of alpha is not 0 or 1, then all these zeros will become distinct. And then if you have infinitely many distinct zeros, then that polynomial must be the identically zero polynomial. Now, in case the magnitude of alpha is equal to 0 or equal to 1, then you have to consider something else and you have to conclude what the polynomial is. That is basically the hint for solving the question. I think you should take a screenshot or write it down, or the video will be recorded obviously. So you can discuss about this question in the WhatsApp group. I will leave it to you. But the hint is, I think, enough to solve the question. So we will go over to the next part, that is Vieta's relations. So I wanted to discuss the derivation of Vieta's relations, but since we have some time constraint, I won't discuss it right now. Basically, the idea of the derivation is to compare the coefficients both sides. But anyways, I think you have done Vieta's relations in a previous class, right? Only for quadratics. Okay, so I think in the notes there is the expression for Vieta stations written. Okay, we have not had a class for it. Anyway, so I think this is important. That's why I think I will cover this here only. Although we have some time constraint here. So suppose that Vieta theorem and Vieta station same. So you did only for quadratics. Anyways, so let f be a non-constant polynomial. So if f is a non-constant polynomial, say of degree n, then it will have n roots, maybe with repetitions. So f of x can be factorized as an times x minus alpha 1 times x minus alpha 2 and so on up to x minus alpha m, where alpha is at the roots of it. Now we need some patience to expand this product. Let us try to expand the product. Let us consider a simple case first. Since you did for quadratic, let us consider the quadratic case first. So suppose, look at the chat. Suppose you have a times x minus alpha 1 times x minus alpha 2. Suppose you want to create you want to find out the term with the x in it when you expand this product. So what should be the x term? So if you have done for quadratics, you should know this. What should be the x term? If you expand a times x minus alpha 1 times x minus alpha 2, then what should be the term with the x? The x power 1 term. What should be the coefficient of that term? Okay, right. So how did you arrive at this expression? Obviously, you can do it by expanding, but what I want you to do is I don't want you to expand blind. I want you to directly tell the answer just by looking at the expression a times x minus alpha 1 times x minus alpha. So what you have to do is you have to choose x from exactly one bracket, and from the other bracket you have to choose the alpha. If you want to consider the x term, you have to choose x from the first bracket and minus alpha 2 from the second bracket, and you have to choose x from the second bracket and minus alpha 1 from the first bracket. So that's why you get this minus alpha 1 plus minus alpha 2 and into an a, because there is a leading coefficient a. So similarly, if you want to create the x squared term, you cannot choose any alphas. You have to choose x from each of these brackets. So a typical term of the form x squared will be a x squared. Similarly, if you want a constant, that is, you don't want any x there. That is, you want the coefficient of x power 0. Then what you have to choose is you have to consider a times alpha 1 times alpha 2. How we got that is very simple. We are not choosing x from any of the brackets. We are choosing minus alpha 1 from the first bracket and minus alpha 2 from the second bracket. And there is an a in the beginning. That's why you get a times alpha 1 times alpha 2 for getting the constant term. So similarly, suppose you want to extend the idea to a cubic instead of a quadratic. That is, you have x minus a times x minus alpha 1 times x minus alpha 2 times x minus alpha 3. So now, if you want to get, let us say, suppose you want to get the x squared term. How should you get it? Write down the x squared term. Keep in mind, you have to choose x from two of the brackets and the alpha from the third bracket to get a typical x squared term. While expanding, you will get basically three terms with x squared. So how does a typical x squared term look? Keep in mind that there will be three. You can first try out by entirely expanding the expression and find out and then get the intuition. Correct. So how did you get it? Write down in the chat. How did you get this minus alpha 1 plus alpha 2 plus alpha 3 into a into x square? While expanding, you get basically three terms. What does a typical term look like? You want to create x square by multiplying. So from the first two brackets you choose x, and from the third bracket you choose minus alpha. Then you repeat the same argument. From the second and third bracket you choose x, and from the first bracket you choose minus alpha 1. And then again from the first and third brackets you choose x, and from the middle bracket you choose minus alpha 2. That's how you get minus alpha 1 plus minus alpha 2 minus of alpha 1 plus alpha 2 plus alpha 3 into an a, because there is a leading coefficient of a, and then x square. So do you get this argument? I mean, does everyone get this argument? So everyone should reply, otherwise I won't know if everyone gets the argument. So I want more people to reply, otherwise, okay. So using the same idea, what should be the x term? How will you create the x term? A times x minus alpha 1 times x minus alpha 2 into x minus alpha 3. You have to, a typical x term will have something of the form c into x. So if you want something like c into x, you have to choose x from exactly one of the brackets and alphas from the remaining brackets, minus alphas from the remaining brackets, rather. So what should be the term with the x? So I will write down the term. I hope you understand. It should be a times, yeah. So actually, yes, correct. So it should be a times alpha 1 alpha 2 plus alpha 2 alpha 3 plus alpha 1 alpha 3. So basically what you did is that, forget about the a, you want an x term. So from the first bracket let's choose x, and from the remaining two you choose minus alpha 1 and minus alpha 2. So you multiply them, you will get alpha 1 alpha 2. So one such term with the x will be a times alpha 1 alpha 2 x. Similarly, we go for the other terms. You choose x from the middle bracket, and you choose minus alpha 1 and minus 3 from the first and third brackets. So that term will be a times alpha 1 alpha 3 into x. Similarly, you choose x from the third bracket and minus alpha 1 and minus alpha 2 from the first and second brackets. So you get a times alpha 1 alpha 2 x, and then you add them up. You get a times alpha 1 alpha 2 plus alpha 2 alpha 3 plus alpha 1 alpha 3. So does everyone understand this clever argument, rather, I should say? That is, without exactly expanding the entire thing, we are trying to just guess the answer just by looking at the polynomial. So everyone should answer. So I want a few more people to answer, because there's a bit complicated argument. So, okay. So now we go over to the general situation. Now that you have understood the special cases, general situation becomes easy. Let's expand the product. So in this, n times x minus alpha 1 times x minus alpha 2 up to x minus alpha n, we want to create the x power k term. So we need to choose x from k of the brackets and n minus k of the alpha i's from the remaining brackets. But that's not enough because we also have a minus sign with each of the alpha i's. Correct? So we get an extra factor of minus 1 power n minus. And there is already an an in the beginning. That's why the coefficient of x power k will be this summation. Forget about the summation now, just look at the expression. Typical term of the term having x power k looks like this. Is you have minus 1 power n minus k into alpha I1 to alpha I2 up to so on alpha In minus k into a. How did we get this expression? Basically, from the I1th position, I2th position up to In minus kth position, we chose minus alpha I. And from the remaining positions, we chose x. And that's why we chose k times, x multiplied k times. So we got an x power k. And the coefficient is minus alpha I1 into minus alpha I2 and so on up to minus alpha In minus. So when you write it as shorthand, you get minus 1 power n minus k into alpha I1 into alpha I2 up to alpha In minus k. But again, there is a leading coefficient an in the beginning. That's why you have an into an. Now, we had done this by fixing the positions I1, I2 and so on up to In minus k. So just as we did in case of quadratic and cubic, now we have to sum over all possible choices of I1, I2 and so on up to In minus k. So this is the expression for coefficient of x power. So does everyone understand this general argument? If you don't understand, it is okay to write down, or maybe you want to unmute and ask. But I want a reply from everyone to understand. Whether you understand or not. So more people should reply. There's nothing to be shy. It's okay because this is a very difficult thing to do in the general case. When I don't remember the general case, every time I do it, I have to rederive it. But once you understand the argument, deriving it is easy. Okay, so since I assume everyone understands, now I'll move on to the next slide and we will derive the general case of Vieta's relations. So now, if we denote the coefficient of x power k by ak, then we directly get Vieta's relationship. Ak equal to summation over all possible choices of I1, I2 and so on up to In minus k. And the thing that we are summing up is an times minus 1 power n minus k into alpha I1 into alpha I2 and so on up to alpha In minus. So now if we want only this thing, that is summation over alpha I1 into alpha I2 up to alpha In minus k, just by rearranging the equation a bit, we get minus 1 power n minus k into ak by a. Mind it, n is the leading coefficient, that's why it is not 0, and hence dividing by it is valid. So in shorthand, or let's say not exactly in shorthand, we can remember this in this way. Suppose we want the sum of product of roots taken n minus k at a time, and that is equal to minus 1 power n minus k into ak by a. So this is the general case of the Vieta's relation that you saw in the quadratic case. Do you understand this final expression? Everyone should answer. because this is a bit complicated, I agree. Okay, so that aside, as I said earlier, even I don't remember this expression every time I do it. So maybe for quadratic and cubic I remember, but then for higher powers I will forget. So every time I have to solve a question using Vieta's relationship, I try to rederive it, because in most cases you don't need to deal with the general case. In most cases, your the degree n will be given, so you have to deal with something like n equal to 2, 3, or 4. So it is, I think it's not necessary to really remember this expression. What you have to do is you have to go over that entire argument. So write f of x as a, and say we are doing with x equal to 4. So write f of x as let's say a4 times x minus alpha 1 times x minus alpha 2 times x minus alpha 3 times x minus alpha 4. And then what you need to do is you just need to multiply the whole. Either multiply the whole thing by hand, or you just do the argument that we did just now. That you have to choose, if you want to get the coefficient of x square, choose x's from two of the brackets and minus alpha is from the remaining brackets, and then you get the x square. And then you have to equate this x square term to the coefficient of x square on the left hand side, and then you will easily get the expression. So what I mean to say is, this is the general argument, you don't need to remember. So I hope everyone is clear. So just for being sure, let me ask, can you all do the derivations for individual cases right now? Everyone should answer. This is an important thing. So data generation is very important. Okay. So this, once you know Vieta's relationship, believe me, you have a lot of power in your hand, because Vieta's relationship is very useful in lots of problems. In fact, most of the problems you will see in PDF, most of them are a variation of Vieta's relationship. So now let us see an application. So as I promised, I won't remember what can we derive by binomial theorem. Well, no, I mean, you cannot derive by binomial theorem, but the idea using which you derive binomial theorem, that is the same idea. I mean, when you derive binomial theorem, what you do is this, that is, you choose x from k of the brackets and some other term from the remaining brackets, and then you count that how many terms you chose. That turns out to be ncn minus k, that is equal to nck. So the idea used to derive binomial theorem is the same as the idea we used to derive the Vieta's relationship. Or what you can say is Vieta's relationship is a kind of generalization of the binomial theorem. Because in binomial theorem, you consider the polynomial, say x minus alpha whole power n. And here I am telling you to derive for the general polynomial, an times x minus alpha 1 times x minus alpha. Yes, exactly. You take all the roots equal and then you get binomial theorem. So the number of such terms you will get in the summation, that is precisely equal to nc n minus k. And nc n minus k is same as nck. That's why you get that kind of an expression in binomial theorem. So let us go over an example. So I think I have 13 minutes now about, so I will finish Vieta's relationship here. So suppose A, B, and C are real numbers, such that their sum is positive, the sum of products taken two at a time is positive, and the product is also positive. From here, we want to prove that all of them are positive. That is, A, B, and C are all positive. So now, what hints us to use Vieta's relationship? Observe that you have to deal with terms of the form A plus B plus C, AB plus BC plus C, and ABC. So if you remember the expression for the Vieta's relationship in the cubic case, this is precisely the kind of terms you get. So this strongly hints that you have to use something very similar to Vieta's relationship. But again, I don't remember exactly that what Vieta's relationship says in the cubic case. So what I will do is I will try to rewrite it. So for that, I will consider a polynomial x minus a into x minus b into x minus c, whose roots are a, b, and c. On expanding, you get x cube minus a plus b plus c x square plus ab plus bc plus ca x minus abc. So while deriving Vieta's relationship, what we did is we gave this kind of an argument. The coefficient of x cube has to be 1 because we have to choose x from each of the brackets. The coefficient of x square has to be minus of a plus b plus c because we have to choose uh, uh, x from two of the brackets and another term from the third bracket. So if we choose x from the first two brackets, you have to choose minus c from the third bracket. If you choose x from the first two brackets, you have to choose minus b from the second bracket. If you choose x from the second and third bracket, you have to choose minus a from the first bracket, and then you get minus a plus b plus c x square. Similarly for ab plus bc plus c x, and similarly for minus abc you get because you don't want any x in the last term, so that's why you choose minus a, minus b, and minus from all the three brackets. So you expand it in this way. So now what does the condition say? Condition says that a plus b plus c is positive, ab plus bc plus c is positive, and abc is positive. And we want to prove that a, b, and c are all positive. But a, b, and c are nothing but the roots of this polynomial. So we want to prove that the roots are all positive. How do we prove that? Let us suppose that the root is not positive. It has a non-positive root. So if it is not positive, only two possibilities are there. It is either 0 or negative. So if you substitute x equal to 0, does it give you 0? It won't, because if you substitute x equal to 0, you will get minus abc, and minus abc is negative, right? So if you substitute x equal to 0, you do not get 0. That's why 0 is not a root. So is any negative number its root? Let us see if you substitute a negative x here. So if x is negative, x cube is also negative. X square will be positive, but minus of a plus b plus c x square will be negative. Then again x will be negative. That's why ab plus bc plus ca x will be negative. And the last term is minus abc, that is negative. So if you sum up negative numbers, you get a negative number. So f of x will be negative if x is negative. So it cannot be 0. So a negative number cannot be the 0 of the polynomial, cannot be a root of the polynomial. So any number which is a root of the polynomial must be positive. And that's why, since a, b, and c are all roots of the polynomial, each of them must be positive. So do you understand this argument? And do you understand the motivation behind repeating the proof of Vieta's relationship? Do you understand why suddenly we started to repeat the proof of Vieta's relationship? Like what motivated us? Okay, so basically the motivation was we are considering these expressions: sum of roots and sum of products of roots taken two at a time and product of roots. Now you can generalize this idea very easily. If you have four terms now instead of three, a plus b plus c plus d is positive, ab plus bc plus ca plus ad plus bc plus da, etc. Everything is positive. And then you take three at a time, that is abc plus acd plus bcd, etc. That is positive, and abcd is positive. Then by repeating the exact same argument, you can conclude something about a, b, and c. So I will confirm once again, everyone understands the motivation. Okay, I want everyone to reply because I want to know whether everyone understands this motivation. This Vieta's relationship idea is very important. Okay, the motivation. Observe that you have terms of the form a plus b plus c, ab plus bc plus ca, and abc. So when you derive Vieta's relationship, you have to keep that expression in mind, that final expression you get. You have to keep the picture in mind. You might not remember the exact position of the alpha I1, alpha I2, and so on. But you have to at least give an intuition of what you are doing. In Vieta's relationship, what we did is that we took sum of products of the roots taken k at a time. So when you expand the whole thing, how does it look like? You consider terms of the form a plus b plus c plus d, ab plus bc plus cd plus da plus ab plus and so on, and then you take three at a time, abc plus bcd plus adc and so on, and then you take four at a time, and four at a time means abcd. And similarly, if you are dealing with five terms, you will have a plus b plus c plus d plus e, and if you take two at a time, you will have ab plus bc plus cd plus da plus ae, etc. More terms will be there. I think I'm missing out something. And if you take three at a time, you will get ABC plus BCD, etc. So you are taking basically sum of products taken K at a time. And in the question, we had exactly something of this form. We had taken sum of products taken one at a time, that is sum, and sum of products taken two at a time, and sum of products taken three at a time. And that's why we were motivated to repeat the proof of Vieta's relationship, because that is exactly what Vieta's relationships give us. So do you understand the motivation now? Okay, so I hope everyone got it. And so, Kwanit, how much time do we have left?
4 minutes.
4 minutes. So there is nothing much we can do right now. We have to continue in a different class. I expected that because these topics are a bit complicated than what you have. So I will leave you with just two exercises which you can try out on your own. So given that the sum of two of roots of the equation 4x cubed plus ax square minus x plus b is 0, where a and b are rational numbers, solve the equation for all possible values and a and b. That means a and b are not given to you. All you know is that a and b are rational, and you have three roots, alpha, beta, and gamma, and say alpha plus beta is 0. Then use Vieta's relationship to solve for the roots alpha, beta, and gamma. And then you have another question is find a and b such that the roots of the equation x cubed plus ax square plus bx minus 8 equal to 0 are real and in geometric progression. So I think most of you know geometric progression because it is, I think, there in class 9 in CBSE. Or I will just write down what a geometric progression means. It means a series, or not a series, a sequence of the form alpha, comma, alpha into r, comma, alpha into r square, etc., where alpha and r are non-zero. You cannot have 0 for the terms of a geometric progression. And we are considering finite geometric progression. That is, you go up to some alpha into r power k. Basically, you find all a and b such that the roots of this equation are real and are in geometric progression. That is, roots are precisely of this form. There will be three roots. So basically, you want roots of the form alpha, comma, alpha into r, comma, alpha into r square. Now you know the coefficients and you know how the roots look. So now all you have to do is you apply Vieta's relationship. So does everyone understand the question? The two questions? So as again, I'll tell you as before that you don't need to remember the relationship. You can just rederive it. Just keep in mind that there is a leading coefficient in the beginning, and all you have to do is consider x minus alpha 1, x minus alpha 2, and so on, and you can rederive the whole thing. So if everyone understands the question, I think class will end soon, so I won't go into any